11,000 volts. Turn up the voltage. Looks pretty good. And that's 11,000 volts. Turn up the voltage. Looks pretty good. That was pretty cool, wasn't it? Today, we will be studying the basics of using AC power to provide a simple model for a space ion drive, which consists of a copper tube inside of an aluminium tube, like a Corbino disc, and a wire electromagnet around the outside. And then argon gas comes in from here through that tube, between the copper and aluminium, gets ionized by high voltage AC, and spins when we get a magnetic field and Lorentz forces from this electromagnet. Now that electromagnet is going to be driven by a little 24 volt garden power supply, which goes to about 10 amps. And the argon gas comes from this cylinder, so all we need to do is worry about where the 11,000 volts of AC power is coming from. If you trace the wires back here, you can see it comes from this huge power supply built from 5 microwave oven transformers. Each one gives about 2200 volts at 240 volts on input, so 11,000 in total. So, given all these switches, we're going to try AC power to make an ionized arc of argon and make it spin using the electromagnetic forces from this wire coil. I've already done this with DC and permanent magnets, which are DC, and I've also done it with pulse DC. This is what we're doing with AC. Now the thing here is the AC 50 Hertz signal going into here has to be in phase with the AC 50 Hertz signal here, or otherwise it won't work. Let's go ahead and do the experiments and see what happens. Turn off the electromagnet, turn it on again. So we're clearly getting a sync between the 24 volt signals going to this electromagnet at 60 Hertz and the 11,000 volts coming out of the power supply. Now this is with a 40 microfarad run capacitor, a slightly larger aluminum copper disc with an electromagnet, and we've got the 400 microfarad capacitor over here. We turn off the magnetism, nothing. Turn on the magnetism. Without the capacitor there, it spins the other direction. No capacitor. So the capacitor can change the direction in which this disc spins. Now we have a 50 microfarad run capacitor, a slightly larger aluminum copper disc. And we have a 400 microfarad capacitor to shift phase. Turn it off. Electromagnetism, turn the coil back on. When we take off the capacitor, it spins a bit more weakly in the opposite direction. Turn the electromagnet off, turn the electromagnet back on. Conclude, we have successfully today, for the first time, produced spin motions of ionized argon gas between these copper and aluminium electrodes using this electromagnet. Now, that alone does not shoot the ions out. However, if we change this magnetic field slightly so it's not only axial but also radial magnetic fields, then when it starts spinning, the ions will shoot out. So we're well under our way to making an AC ion drive, and that's what we'll do in the next experiments. It's with the low resistance choke of about 30 millihenries, phasing it the other way from the capacitor. Now, in addition to using an axial electromagnet, we can also use 3-wire coils arranged triangularly around the Corbino disc to make what's known as a radial electromagnet. All of these will have the same AC powers in the disc. Now, to do that, I'll get 11,000 volts out of these 5 microwave oven transformers, which are powered by this isolation transformer and a variac. And then for these radial electromagnets, I've got another isolation transformer with a little fan motor controller, which controls how much power goes into these radial electromagnets at about 60 volts, 80 volts. Let's turn it on and see what happens. Now, these are the 3 radial electromagnets with a 400 microfarad capacitor in the electromagnet circuit. Turn on the magnetism, we get a little bit of spin motion beyond where they are. Not all the way around, however. When we remove that capacitor from the electromagnet circuit, control the magnetism, we can again see a partial arc, maybe going the other direction, but not all the way around. The magnetic fields here all point inward rather than north and south, so we're not getting enough spin motion from inward pointing magnetic fields alone to make it spin. These are 5 microwave oven transformers lined up in series in their secondary coils, in parallel in their primary coils, and I've got an isolation transformer for 240 wall power and a 50 microfarad run capacitor. Let's see how much power it gives in this spark gap. That was pretty cool, wasn't it? That's enough for now. No one should do this unless they know electricity very well. This Perspex box is a very important safety aspect because those transformers are live if you touch them. If you trace the wires back here, you can see it comes from this huge power supply built from 5 microwave oven transformers. Each one gives about 2200 volts at 240 volts on input, so 11,000 in total. So the outputs of those microwave transformers are all wired in series, so the voltage add is 5 times 2200, and they output 11,000 volts through these 2 wires on each end. The inputs to those microwave transformers are here. There are 5 of them in parallel on the primary coils, and they go through this run capacitor, which can vary from like 20 to 50 microfarads to control how much 240 volt wall current at 50 hertz goes through it. 50 is a lot and 20 is not very much. In order to power those safely, we have an isolation transformer which gets plugged into the wall which we can switch on and off, and a variac, which is plugged into the isolation transformer to control how much voltage from 0 to 240 actually goes into that run capacitor, gets through and gets in the microwave transformer.